Hello once again, this is an INB382 demonstration video, and in this one we're going to look at Brdfs, bidirectional reflectance distribution functions. Apart from being a reasonably long acronym, these are rather Jim Dandy shaders for producing these really cool effects on the surfaces of objects. You can see here, of course, a gold object. We can see here an isotropic shaded object, and here is an orange, and here is something made of bronze. So the beauty of this is that we can start to play around with having much more complex functions of light across the surface of objects. Mathematical gobbledygook, but in the end this means that these objects start to look more realistic, and we can start to add much more impressive graphics to our games. In particular, think about it this way. A lot of games have gold and bronze objects in them. Just any sort of picking up of gold objects as part of prizes or loot, blah blah blah, or even the appearance of satin and brush metal objects. These things commonly appear in games. If you want something to look this way, then you need to have something. You need to have a lighting function that's much more complex than Phong and Gura. So this is where we show a very cheap technique for doing this, just so that you get an idea of how this works. Alright, so moving right along. First of all, let's have a look at what we've got here. So I've gone through. We've got bronze, gold, an isotropic metal or satin, and an orange skin shader, just for arbitrary's sake. We can see down here that all of these, as I say in the lecture, are just the multiplication together and scaling of values from two environment maps, G and H. So as you can see here, they're just materials. They're just like any cube map shader. So it's similar to a cube map shader. You need cube maps. You need two for each material. Nothing wrong with using more than one texture. This is where texture blending comes in. So just showing here, this is the G function for the anisotropic shader. And we see here that the bottom and top effects giving sort of a glow effect to the shading. And we can see that there's very much a horizon here. So for the G function, we're looking above, we see that sort of a glowing effect on the surface. So this sort of approximates diffuse, but it's not really. Really what's happened is that a deformed reflectance function has been linearly separated into two functions, a G and an H. But when we do look at the H function, we see it does sort of resemble a specular component. But remember, these two functions have elements that are not really sort of intuitive to us as humans to read. Multiply them together and you get this final effect. The same with gold. So if we look at the gold over here, aniso gold, we see here that the G function is just basically above the hemispherical top part of the surface. It has a sort of this glowing effect. It's gold. And when we go to the H value for gold, we see here's the specular component modeled in, and some other diffuse components. So again, it sort of approximates it, but it's not really. And so once we multiply these together, we get the gold effect, as we see here. And that makes it quite a pleasing sort of gold-like environment. So again, just to also note, as you can see, that these are cube maps, so there's separate elements for each one. And just like before with the other cube maps, you can select the planes of the cube, so to speak. I won't modify them for this, just so you understand. You can construct these from the basic resources, which again are here. So these are all the raw textures that I've loaded up for each of the appearances, the Brdfs. Now to do this, let's move across to the shader. So the shader I've lifted from an NVIDIA demo by Chris Wynn. Look for the paper. It'll give you all the theory on the background and is useful. I think I reference it at the end of the lecture. So, this is the basis for this technique developed by NVIDIA years ago. Much more subtle techniques are used now with a similar approach, just modeling the reflectance of objects in an arbitrary manner. So going through this demo here, we see that properties, there's the two cube maps that are coming in, the H and the G. So both cube maps, all good. So standard sort of environment mapping using cube maps. Note here though that the inputs to the vertex shader are slightly different. Now what we should note here is that we're using an orthonormal tangent basis on the surface of the geometry to model these effects. And what we see here is that for the basic environment map, because the effects are symmetrical around the normal, we just needed the normal and we just reflect around the normal. But here we need an orthonormal basis function on the surface that I cover in the lectures. So what we pass in and what Unity will give you is a tangent vector. The tangent at the surface incident at the position. And you get the surface normal that you use for your lighting functions as per typical sort of approaches. The problem is, though, that you need a third vector, which is the binormal. And for whatever reason, in DirectX, you would have the binormals as part of the meshes. It seems Unity, you have to calculate them yourself. So looking down here, we go into the vertex shader, the Brdf. See typical stuff such as just transforming the position via the MVP Unity matrix. And here's where we calculate our binormal for our coordinate system, the normal times the tangent. And then moving on, here's the position in world coordinates, all good. Here's a light value vector that's calculated. And then here's a world space light value. So, all these are straightforward, and a 2i vector. And then this is where we come down and actually calculate a half vector, again, according to the Blinn model of lighting, between the 2i and the 2 light vectors. And then the H cube map, the texture coordinates need to be generated so that we can access the faces of the environment map. So that means that the coordinates generated, we take that half vector we've calculated and we dot product it with the tangent, the normal, and the binormal on the surface. And then we do an inverse Gram-Schmidt process in order to get the correct values for our other coordinate system. So remember, there's a Gram-Schmidt process used to create a linearly separable set of environment maps. A complex concept, you don't have to know it in detail, but you need to just be aware that these two maps have been deformed in order to make them linearly separable. And so once these coordinates have been modified by a Gram-Schmidt process, that T prime, sounds like a wrapper, and B prime are then passed to this set of dot products in order to generate the G. Just change that on the fly. The G cube map texture coordinates here. So those two coordinates are used to access the environment map. And then at that point as well, we transform our normal for our lighting. We do a diffuse calculation, a diffuse value from the normal to the light. All standard, straightforward stuff, just a basic L.N lighting model. And we pass that out as a color. So those are the coordinates that are passed out as variables by VS output, coordinate H, coordinate G. Note their texture coordinates. We have, we're using more than one texture coordinate here. So text coord semantic 1 and a text coord semantic 0 with an implicit 0. You don't actually have to add it and a color. So that's the vertex shader. That's where the correct coordinates vectors are calculated, just like with most cube maps, in order to access the faces of the environment map. When we get to the pixel shader, the Brdf pixel shader here, we then access these cube maps using those generated coordinate functions. And lo and behold, that gives us our two colors, the color from the H function, the color from the G function, environment maps. And then the final output is just the diffuse lighting multiplied by a multiplication together of the H and G components scaled. I just scale it with a value 8. It's arbitrary because what has happened is those coordinates, those environment maps have actually been scaled back. And if you can see here, this function rapidly goes to 0. So they're very dark images because they multiply together. So we just need to bump it up. 4 or 8 is a good number. Play around with it to suit. Once that's done, you get the effects specified coming out of the shaders, and you get this. So you get these very quite attractive looking shaders that give you the appropriate appearances for anisotropic objects. So this looks like a Christmas decoration, as though it's been wound together with satin cord. You get this strong directionality to the reflectance and the specular distribution. Whereas, with gold, of course, there's very little anisotropy. There's a bit, but very little. And we can see that this glowing effect that occurs. So it's much more glowy compared to Fong and Guro. Here we have bronze. Again, we can see that it's orange, sort of orangey. It's starting to head towards an orange color. It's not as yellow as gold. And so we get bronze. And then moving on down, this is an orange. Now, interestingly enough, note, for the orange, I find it gives you probably this sort of glowy appearance that an orange generates. You've got to mix it up with a normal map. You then may wish to add some dirt to its surface. You have a look at an orange in a supermarket. Fine, that's the reflectance of light on the surface, but you then have to add the details on to make it look like an orange. So be aware that these are components, these are layers, so to speak, and you can use them. You can sort of mix and match the satiny effects or the brush metal effects together with, gold. So you maybe, I guess with bronze is an example where, that tends to get verdigris on it. It builds up layers of crud on it, so to speak. You see that in statues and whatever. What that means, you're going to have to blend in some sort of, verdigris style effects on the bronze rust and dents and all sorts of things to get the final appearance. But as you can see here, these reflectance distribution functions, bidirectional reflectance distribution functions, give us something that approximate the appearance of these properties for materials. And it makes the visuals in our game or our virtual environment appear just that much better. Okay, thank you. That is the end of the video.